Welcome. For a parallel RLC circuit, this video explores a specific circuit example with emphasis on intuition for how the circuit behaves. Here is the parallel RLC circuit and the voltage equation 14.165b for the underdamped natural response due to the initial condition inductor current I sub L naught.
Notice how we have three currents in the circuit, but there is only one voltage, and it goes across all three components in parallel.
The differential equation 14.18b uses voltage as the circuit variable, and equation 14.165b is the final solution voltage. The inductor instantaneous current value, due to the initial condition at time 0, is 300 milliamps. The downward arrow in the schematic on inductor current indicates positive polarity relative to the voltage reference polarity.
We'll explore three topics in this video.
First, does a higher resistance value damp the circuit more or less? And how does the answer make sense intuitively? Second, looking at the voltage equation 14.165b, what do we expect the voltage signal shape and polarity to look like? Third, what do we expect the capacitor and resistor instantaneous current values to be at time 0 and why?
Section 1. Resistance and underdamped response.
The values of the resistance are the inductance L and the capacitance C, which make up the roots in equation 14.42a, determine which of the three damping responses the circuit will have: overdamped, critically damped, or underdamped. Equation 14.60b gives the criteria for underdamped response. When equation 14.60b is true, the quantity under the square root sign in equation 14.42a is negative, resulting in complex conjugate roots indicative of underdamped response.
Much of the content in this video is based on Chapter 14 in this book, called First and Second for short. The equation numbers in this video, starting with 14, are the exact equation numbers in the book for your reference.
Making a new design, we could use equation 14.60b to check to see if our choice of values of R, L, and C would give underdamped response. Plugging in the specific values of resistance, capacitance, and inductance from the schematic into equation 14.60b, and then calculating with equations 1 and 2, we see in equation 3 that the inequality is satisfied and that the schematic shown will exhibit underdamped response behavior. The decaying sinusoidal voltage in the simulation graph illustrate underdamped response. The decay corresponds to the sigma term in equation 14.68b, and the oscillation frequency corresponds to the omega sub d term.
Okay, but how does resistance affect damping? Does higher resistance mean more damping?
Good question. Let's look more closely at the roots equation for the underdamped case. When the inequality in equation 14.60b is true, a j term comes out from the radical sign as shown in equation 14.64b. J is the complex operator. Then the square root quantity becomes omega d in equation 14.65b. The minus 1 over 2 RC term is sigma in this case. Notice how the resistance term R in the denominator of the real term of equation 14.64b means that higher resistance lowers damping. Less resistance means more damping. In the resistance parameter sweep simulation plot, the 150 ohm resistance corresponds to the lowest current signal amplitude and more damped inductor current curve. The tallest, least damped curve corresponds to the 500 ohm simulation. Let's look at resistance and damping from the schematic point of view. As resistance in the parallel RLC circuit increases, less current goes through the resistor, which means more current oscillating between the capacitor and inductor. Less current being dissipated means decreased damping. In the extreme of high resistance, the resistor effectively disappears, leaving an open circuit and an ideal undamped LC tank circuit. With much higher resistance, 1000 ohms in this simulation, the damping is much lower. There is only a small amount of exponential decay in two currents from 0 to 7 microseconds in the simulation.
Section 2. Voltage, signal shape, and polarity.
The question is, what voltage signal shape and polarity do we expect to see based on the time domain natural response voltage equation 14.165b for this RLC circuit? Based on the sine omega d term in equation 14.165b, we expect to see something like a sine wave as shown in the graph. But what polarity do we expect? Will the RLC voltage sine wave start out going up, like this graph of a pure sine wave? We expect a voltage signal that looks like a damped sinusoid starting at 0, like a pure sine wave equals 0 at time 0. Noticing the minus sign at the beginning of equation 14.165b, we expect the voltage to start out going negative, like we see in the voltage plot of the underdamped parallel RLC.
Section 3. Instantaneous current values and the resistor current.
Here are two questions we want to answer. First, what do we expect the resistor current to look like? Second, how do we know the instantaneous values of the capacitor and resistor currents at time 0? For the resistor current, we know that it is related to the voltage by Ohm's law. This means that the resistor current will have the same shape as the voltage. Notice in the simulation plot, the green current plot is sitting on top of the voltage plot. You can't even see the red voltage plot line at all. but you can see the red voltage label on the left side of the plot. This simulation plot also answers part of question 2. The instantaneous value of the resistor current is 0 at time 0 because the voltage also starts at 0. We know that the initial condition inductor current means that the instantaneous value of I sub L 0 at time equals 0 will be 300 milliamps. What will the capacitor current be? How do we know this? We know that the resistor voltage and current are 0 at time 0. This means that the instantaneous inductor current all goes up into the capacitor at time 0. The instantaneous capacitor current at time 0 is minus 300 milliamps.
Okay, but why can't the instantaneous inductor initial condition current right at time 0 appear through the resistor?
The answer is that the capacitor voltage cannot be changed instantaneously. An instantaneous resistor current means an instantaneous voltage across the resistor and the capacitor. This is how we know that all the instantaneous inductor initial condition current goes through the capacitor at time 0.
We also saw the same principle at work in the parallel RLC Natural Response Voltage Derivation video during the calculation of constants K using initial conditions.
Thank you for watching and learning with us.